Welcome to an introduction to chemistry brought to you by Parkbench Tutors. For more information about Parkbench Tutors, just look us up on Facebook or visit parkbenchtutors.com. In this short podcast we are going to do some revision work on atomic structure, and so this is in the nature of a support tutorial. Let's start with some of the early ideas put forward by a man called Dalton, who put forward the first atomic theory, which said that matter was made up of atoms, that the atoms of any element were alike in weight and they differed from those of atoms of other elements. It was the atoms that took part in chemical changes and they formed compounds, but the compound had different properties to the atoms that it was composed of. And the weight of an atom remained a constant even when it was part of a compound. Remember, these were the first ideas. Following on from that, various stages are recognized. Thomson was the first to discover the first subatomic particle, which he called the electron, and he found a ratio of the charge to the mass. It was, however, a man called Millikan who was first able to determine the actual mass of an electron as 9.11 times 10 to the minus 28 grams. Rutherford then did work with the nucleus, and he showed through work with alpha particles that you had a nucleus, which was where most of the mass was. The nucleus had a positive charge, the electrons of course were negative, and that he called the positive charge particles protons. And he also predicted that there must be some particles in the nucleus that didn't have a charge, and he called those neutrons. They would have a mass but no charge. So that led to the idea of Niels Bohr's first atomic model, which had a dense nucleus with a positive charge surrounded by electrons which were in orbits, and the orbits he referred to as shells or energy levels, and he predicted there would be a maximum number or limiting number of electrons in each of the shells. If an electron was close to the nucleus, then there was less energy needed to hold it there, but the further away from the nucleus an electron was, the more energy was needed to move from one shell to another. So if we have 5 principal energy levels, we can see that the number of electrons in each level is different, and it tends to increase: 2 in the first level, 8 in the second level, 18 in the third, and so on. So of course the next stage was to look at how this number was made up. We knew at this stage that we had an electron with a negative charge, a proton with a positive charge, and a neutron with no charge, but the proton and neutron had the same mass, which we'll call the relative mass, and that the electron had a much smaller mass. We're not looking at subatomic particles that have been discovered since then, because chemistry depends by and large on an understanding of electrons, protons and neutrons. So using that Bohr model, we can say the electrons are in shells, the protons are the atomic number, and the number of protons for an atom, or for all atoms of the same element, will be the same. So atomic mass is used rather than trying to express things in grams, and we base our idea of atomic mass as atomic mass units, and 1 unit is 1/12 the mass of a carbon-12 atom. The sum of the protons and neutrons in the nucleus is the mass number. Sometimes you get elements that have got different masses because they have different number of neutrons. Now if they're atoms of the same element, they'll have the same number of protons, but they can have differing numbers of neutrons, and if that happens we call these isotopes of the element. If we look at the table then just of the first 10 elements, we can see that the atomic numbers go from 1 to 10. The number of protons will go from 1 to 10. The number of electrons will also go from 1 to 10, but we can see that the number of neutrons can in fact vary. So the first atom with neutrons is helium, which has 2, and then you have lithium with 4, beryllium with 5, with boron and carbon have 6, so you can see neutrons aren't going up in the same stepwise manner that protons and electrons are. Now if we look at the energy levels of the electrons, then we say there are different energy levels. The first energy level can have 2 electrons in it. Once it's got 2 and you can't have any more. The second energy level can have up to 8, and then it stops and you start building the third energy level. So, and this is done of course in the order of the atoms in terms of atomic number. So hydrogen, helium, lithium, beryllium, boron, and so on. So, are there any other ways in which we can represent electrons? Well, there are, and they're frequently used. We can have little pictures which suggest that you've got this little central nucleus for hydrogen with 1 proton, and you have an electron whizzing around it in a circle. And if you take the next element, helium, with a nucleus with 2 protons and 2 neutrons and 2 electrons whizzing around it in a circle. What you have to remember though is that this is actually just a representation. And it's a representation to give an idea of shells around a nucleus. Let's consider the valence of elements. So atoms form compounds by attempting to complete the outer energy level. And so the electrons in the outer shell are the valence electrons. The number of electrons that are gained, lost or borrowed has become known as the valence of an atom. So if we lose electrons, then the valency number is given a positive sign, which is also the oxidation number. And if we gain electrons, we have a negative sign for the oxidation number. So there are a number of representations in common usage to show the outer shell. So here's one typical representation of the outer shell, showing the electrons as dots. But we could also represent it by showing the shells at different levels. So that shows it as 2 in the first level, 8 in the second, 7 in the third, where the outer shell 7 will represent the valence electrons. And the other method where we show our 7 dots, our 7 electrons, is the Lewis dot structure. So to complete that outer shell in the Lewis dot structure, we would need 1 more electron. So chlorine would is said then to have a valency of 1, because it normally takes up 1 electron to complete that outer shell. So the oxidation number becomes -1. Now if we look at sodium, sodium has 1 electron in the outer shell, which we could represent the outer shell if you like as 2, 8, 1. First shell 2, second shell 8, third shell 1. So 1 is the valence electron. So our Lewis dot structure would simply be a sodium kernel with 1 dot around it. And sodium will tend to lose this electron to have stability of just 2 and 8. So the oxidation number for sodium is +1. So let's just consider this idea of oxidation number then. Free elements have an oxidation number of 0. Hydrogen will normally have an oxidation number of +1, but it does form metallic hydrides where you get an oxidation number of -1. Oxygen typically has an oxidation number of -2, but that can change in peroxides and with certain other compounds. What about metals and non-metals? If atoms have a tendency to lend electrons, then they're classed as metals. If they're the atoms that receive the electrons, they're likely to be non-metals. Those that neither lose or gain electrons are the noble gases. And the fewer electrons that an atom needs to borrow or lose, then the more reactive it does tend to be. Nowadays, chemistry looks more at properties which can be recognized through studies of atomic spectra. So Bohr's idea then was that an electron could move from one level to another, and that was a change in energy in doing that. So if you go from the ground state to an excited state, then there must be an absorption of energy. But if you move in the other direction from the excited state to a ground state, then there will be an emission of energy. We can say that the change of energy for the electron is equal to the energy of the final state minus the energy of the initial state. Typically for a mole of electrons that works out as 313.6 kilocalories for each energy level. Right, it's important to understand that energy is released in discrete amounts, and that occurs when there's a change from one energy level to another. So if we change to the ground state, then emissions normally of ultraviolet radiation, and they occur then when an electron moves to the ground state. So electrons moving to the ground state form what are called the Lyman series in the spectra. It's a series of lines. And if they move just down to the second level, then the emission is in the visible range, and that's called the Balmer series. If they move down to level 3, then the emission's in the infrared range, and that's called the Paskin series. So spectroscopy then becomes quite an important part of chemistry. It helps us identify atoms. Emissions of light then are measured with a spectroscope, and they relate to these discrete amounts of energy, because discrete amounts of energy are associated with particular wavelengths of light. There's also something called mass spectroscopy, and that refers to the bending of a beam of ions passing through a magnetic field, and that can be used to determine atomic structures. It can also be used to determine isotopes and to give an idea of the amount of each isotope. Bohr's theory then is based on mechanics, but of course the problem with Bohr's model is that it can't really cope with the idea of discrete energy changes. Newton's idea suggested that for a body, kinetic energy could change smoothly and continuously. This doesn't really agree with what we've just seen in spectroscopy, where we talk about our packets of energy. It was Planck who first suggested that light could have both wave and particle properties, and Vogel suggested that particles could then behave in the same way. And it was shown that electrons could produce diffraction patterns, which was a wave property. So we now look as if we've got a link here. A man called Heisenberg then predicted that you can't know the position and the velocity of an electron at the same time. And from this we developed the idea of a wave mechanics theory, where we had wave functions called orbitals. So orbitals showed the probability of where an electron might be found. And orbitals can be described in terms of quantum numbers, and each orbital has a set of 4 numbers. The principal number refers to the distance of the orbital from the nucleus, so it can be 1, 2, 3, 4, 5. The secondary number, quantum number, refers to the shape of the orbital, and we define these in terms of letters S, P, D and F. The third quantum number is the magnetic number, and it refers to spatial orientation, and the last of the quantum numbers refers to the spin of the electron in the orbital. So we can see from this diagram then that in the first orbital we can have 2 electrons, and in the second orbital we have more electrons, and so on. Now, Hund's rule of maximum multiplicity says that where you get more than one orbital, such as the 3p orbitals, then you put in 1 electron into each orbital first of all, and then after that then you start pairing up the electrons in the orbitals, and that's called Hund's rule. And you can see Hund's rule operating here if you look at the orbital notations again of the first 10 elements. The order of filling the orbitals, this doesn't depend on numerical order, it depends in fact on energy levels. So if you look at this, you can see that the 4s level is below the energy level for 3d, so 4s will fill as an orbital before 3d will. Let's go back to Lewis dot notation for a minute, because that's how we used to simplify the electron notation, where we just show the outer levels. So potassium has a nucleus, and the valency electron is the one in the outer level, which is the 4s1. Arsenic has 1, 2, 3, 4, 5 there. 3 are at the 4p level, and then 2 will be at the 4s level, and so on. Strontium just has the 2, and iodine then has 7. An exception to this is the transition elements, where the elements involved with the filling of the d sublevel take place. Right, from all these studies was built up the idea of a periodic table, and the very first idea of a periodic table was proposed a long time ago by a man called Mendeleev in 1869, and he suggested you could build up a table which was based on atomic weights and properties, and that's still the basis that we use today. And if the atomic weight conflicted with the properties, he suggested that we look at the properties first. And although there were gaps in his first table, what he suggested was that we would actually find elements that would fill in these gaps. Later work on X-ray spectra showed that the properties are a function of atomic numbers, and so the basis for the table should be atomic number rather than the atomic mass, and that's what we use today. We define our periodic table in terms of rows, which are called periods. There are 7 of these, and they start with an atom having 1 valency electron, and they end up with the structure of an inert gas. First 3 periods are short, the next periods are much longer, and period 7 is incomplete at the moment, and it's because most of these do not occur naturally. So we have our table, our periodic table of elements, and we'll be familiar with this with lots of diagrams in our books. The columns are called groups or families, and they have related properties. They used to be shown by Roman numerals. Under the UPAC system, the group numbers are shown now as Arabic. We can relate properties then to this table. In general, metals are found on the left of the chart, and the most reactive of these are found in the lower left, whereas non-metals are found in the right of the chart, and the most active ones in the upper right. Noble gases, or the inert gases, are found on the far right. Group 1 metals we normally call alkali metals because they react with water to form bases. So base forming properties decrease as we go towards the right, and acid forming properties increase as we go towards the right. We also have a series in the middle called metalloids, which has got some characteristics of metals and some of non-metals. Finally, let's consider the radii of atoms. Atoms don't normally have a definitive outer boundary, so we have to estimate the size of an atom by describing its radius. And in metals we say that if it's in the solid state, we take the distance between 2 nuclei and divide it by 2, and that's the radius of the atom, which that can be done using X-ray diffraction. If you get covalent bonds being formed, then you measure the distance between the nuclei and again halve it. We find that in the periodic table, atomic radii decrease as we go from the left to right across a period, and they increase from the top to the bottom in a group or family. That ends our revision section, and if you want further information, then just look up Parkbench Tutors on Facebook. We wish you luck in your studies. Thank you for watching, and